Okay, we've got lab one. I'm going to preface this by saying that I haven't made a PowerPoint, so make sure that your audio is working. We'll go ahead and type that in the search right here, just so you know. Okay. All right, so my experiment was, if we can manage to zoom out here. There we go. Okay, so we've got my dad pushing this little toy Tesla. And you can watch it move. This is approximately 1 meter. It doesn't move the full meter, but it's a good scale frame of reference. All right, so there we go with that. So here are some things that we're going to be using. So we know that if the velocity is average, if our velocity is constant, that we're going to have zero net force, and that's modeled here. So the mass of a Hot Wheel is approximately 0.04 kilograms, but that doesn't really matter if your velocity is constant, because your change in velocity is just going to end up being zero, and therefore you get 0 newtons of force acting upon your system. So it's a cool way to conceptualize and really see how we would get constant velocity. Unfortunately, it's really hard to do that in real life because we don't live in a vacuum. So in the model observed, not accounting for any kind of friction from the floor, just kind of like how we would do it on a problem that we get, it would be about 0.036 newtons of force from this video. Okay, so let's start out by talking about the code. Okay, so we've got our position vector here, our velocity vector here, our velocity is constant, this doesn't change. We end up getting our position update formula here, our velocity update formula here. It's equal to each other because it doesn't change. And this is what it ends up looking like. Okay, so we've got a linear position versus time graph, and then a straight up horizontal velocity versus time graph. And this is because velocity is constant, so velocity is not changing, it's not going up. So it stays at right about 0.78, which was the velocity that we ended up deriving from our observed model. So our change in time ended up being 0.867 seconds, and our change in position ended up being 0.672 meters. When you put those together, using the velocity average formula, you end up getting 0.781 meters over seconds. So now, right here, we've got our values from our observed model right here. So our observed model is going to be the blue dots, and our computational model that we ended up getting through Python, through these values right here, and we're talking about this one right here. We're not talking about the velocity. We're talking about this one right here. So we've got a slope that looks very similar to the one that we just looked at in Python. So we can see that it's straight. It was almost the same from the observed model, but not quite. Almost looks linear, not really. That's because we don't live in a vacuum. Constant velocity is almost impossible, or really hard to actually observe. Very rare. But in a computational model, we can correct for human error, and we get this. So it's cool that we can do that with GlowScript. Um, but yeah, I think that the purpose of this experiment was probably just to correct for the human error that we observed, but we ended up using our same values that we derived from um, from our observed model. But the thing is that there are also other forces acting on this little toy car, that being the friction of the floor, uh, etc. So that's the end of lab one. Um, we do have some questions we need to answer. Um, so how many pushes and pulls are we dealing with if we were to get zero net force? So that's basically subtracting uh, all other outside forces, and you're just getting a straight up. If we follow Newton's second law, if there's no other forces acting on a system, then the velocity is not going to change. It'll be constant. And if the velocity is constant, then we know by the momentum principle that we will end up having a zero net force.